So we get x equals y squared. You can plug in like a number for y, see what it spits out for x. You should see a graph like this. Because if you plug in x equals 1, then y could be positive or negative 1. And then we get the line y equals x, which should look something like this. So this would be the region between them. My drawing's not to scale, but here's y equals 9, the line up here. And we're supposed to be revolving this curve around y equals 9, so it's going this way. Let's see, so to make that happen, I want to think about right cylinders that I'd be drawing that are infinitely small, like they're infinitely narrow, like a dime. You could think of a dime as a right cylinder. The height is just very, very small. And the calculus concept there is that we keep getting smaller and smaller dimes. The height keeps getting smaller and smaller. So the dimes are going straight up and down. So the heights are dictated by the x-axis, right? If I was to draw a right cylinder like this, that's not infinitely small. But the height is dictated by how far along we are on the x-axis. That means I want to integrate with respect to x for this problem. Let's put that back there. There we go. So x is my variable that I'm integrating with respect to, because dx is kind of representing that infinitely small height for each of these cylinders that we're drawing. So in order to do that, I need my limits of integration. So I want to know where to start and where to end. The volume problem. So it's the region between these two dots. So if you solve this as a system of equations, you'll get x equals 0 and x equals 1. So 0 to 1 are our limits of integration. You can plug in x in y squared in here because y equals x and solve that equation. So what I want is the bigger volume, the volume that was dictated by the y equals x line. And then I'm going to subtract that by the volume that's dictated by that curved line that we have, x equals y squared. So to find that bigger volume, I don't think we do need, well, it's a cone. I don't know if we could skip calculus probably because it's just going to be a cone because it's y equals x, but we'll do it a calculus way. The right cylinder has a radius of from y equals 9 to here. The biggest the radius can be 9. But it keeps getting smaller and smaller. The radius keeps getting smaller depending on where we are, the x-axis. So for the straight line, we want to subtract that by x because the y distance is the radius, right? So 9 is the biggest distance you can be. Wherever you are on the x-axis, that's the same place you are on the y-axis for this line. So if you subtract those two, that represents this distance from y equals 9 to y equals x line. So that's the radius. We square it and we multiply it by pi. This is the area of the bigger region. We want to subtract that by the integral from 0 to 1 for the smaller region. Pi r in this case is going to be, how many things in terms of x? So I take a square root of both sides. And you'd want to consider positive or negative, but y equals negative square root of x. What would that look like? That would look like this part down here. So we want the y equals square root of x. Okay, so this formula will tell us the distance between, well, actually here, this is what we want for the distance between y equals 9 and this curve. It's our radius for each of those cylinders that we're drawing, right? Because we want to know the y distance from here to here. The biggest y distance is right at the start, the origin, it's 9. But it keeps getting smaller. We have to keep subtracting it by the y distances that are defined by the x equals y squared line. I think we've got everything now. So factor out the pi, and if you expand this, this is 81 minus 18x plus x squared. If we do the same thing over here, factor out the pi, that's 81 minus 9 square roots of x. So that's minus 18 square roots of x plus x. And then integrating term by term, it's 81x minus 9x squared plus x to the third over 3 from 0 to 1. And we're going to subtract that by pi times 81x. And then here, this is a 1/2 power. So when we find the antiderivative, that's going to go up to a 3/2 power, but we need to compensate by putting a coefficient out front, 2/3. And you can check me. If you take a derivative of this term, it should turn back into what we had up here. And then this is x squared over 2 from 0 to 1. Luckily, some of the work gets saved for us because when you plug in 0, it's just 0. So here we've got 81 minus 9 plus 1 over 3. And over here we got 81 minus 18 times 2/3. Is that 15? Yeah. So 12. Because we're plugging in 1 in for x. So we got to have 81 pi minus an 81 pi, so let's just forget about those. Those are going to cancel out. We got, this is going to be negative 9 pi plus 12 pi. That makes 3 pi. So I took care of this, negative 9 pi plus 12 pi, because it's minus a negative 12. And then we got 1/3 pi subtracted by 1/2 pi. So this is 3 over 6. No, sorry. 1/3. That's 2 over 6. That's 3 over 6. So we got 3 pi minus 1 over 6 pi. So that's 18 pi over 6 minus 1 pi over 6. So I get 17 pi over 6.